Hello and welcome to another video. Today we will discuss about the transient response of a second order system. Second order systems are systems which have the differential equation with a second derivative as the highest order. When we look at the differential equation, it will be something like of this form with the highest derivative as the second order derivative. Similarly, when we have a transfer function, the highest power will be 2. So such systems are called order systems. So the standard form of a second order system is omega n square divided by s square plus 2 delta omega n s plus omega n square, where omega n is the natural frequency of oscillation and delta is the damping ratio. We will see the definition of omega n and delta in the next. The importance of transient response. The transient response describes the system behavior as it responds to a change or before reaching a steady state. Suppose you are giving an input to a with a transfer function g of s, and the change is step input. Now the output is something like this. So there is a phase where the output is changing rapidly for the step input. So that phase is called transient phase. And there is a phase where it has settled at some value that is called the steady state phase. Now we are interested in this transient phase. So what behavior of the system, what characteristics of the second order system is defined during the transient phase. Now this is very important in control systems, especially in automotive industry and aerospace industry. So an accurate transient design is required in these industries. So it is a part of safety also for the system. So the key matrices that we are concerned are the rise time, the peak time, the settling time, and the percentage overshoot. So we will see in detail what are these matrices. So rise time is the time for the waveform to go from 0.1 to 0.9 of its final value, the response final value. So that is the rise time. Peak time is the time required to reach first or the maximum peak. And settling time is the time for the response to reach and stay within 2% of its final value. The percentage overshoot is the amount that the waveform overshoots the steady state value at the peak time, expressed as a percentage of the steady state value. Now, as I mentioned in the first slides, the standard form of a second order system is omega n squared divided by 2 del square plus 2 del omega n s plus omega n square. So in that, delta is this term, the damping factor. So based on the value of the damping factor, we have we can classify the system into second order system into 4 different categories. An underdamped system where oscillator responds with a decaying amplitude, a critically damped system where the response is without any oscillations, so it is a fast response without any oscillation. Overdamped system is slow response with no oscillations, and undamped system is continuous oscillation without any decay in the oscillations. We will see how the waveforms will look like in the next slide. So based on the value of delta, we have these 4 different categories. Where undamped system, where the oscillations are not damped, it is a continuous oscillation. So the delta value here will be 0. The oscillations are not reducing as time goes on. The oscillations are not reducing. It is maintained in that oscillatory state. So there is no damping. It is called an undamped system. An underdamped system has few oscillations. So this is the underdamped system response with a few oscillations. In a critically damped system, it is a fast response with just enough, without any oscillations. And an overdamped system has no oscillations, but the response is very slow compared to the critically damped or underdamped. The role of the natural frequency of oscillation, omega n. This indicates the frequency of oscillation for the system in the absence of damping. So the frequency of oscillation, frequency at which it oscillates, the system oscillates, is given by this natural frequency of oscillation, omega n. So this has some impact on the transient response of the system. Higher the omega n, generally the result in faster response. And combined with the delta, it determines the speed and stability of the transient response. Now, what we are concerned is the step input analysis of the second order system. So what is the step input analysis? So when you give a step input to the second order system, you can have different kind of oscillations. So a different kind of output response. It can be oscillatory, it can be critically damped oscillations without any oscillations, or over damped system. So based on the characteristics, we can determine what kind of response we can get for a step input. So this is the standard form of a second order system. We have omega n squared divided by 2 s square plus 2 del omega n plus omega n squared. So based on the roots of this denominator, or the roots of the denominator are called the poles. So based on the locations of the poles, there can be different categories of the system. So when the delta value is 0, so this value delta value is 0, the poles are on the imaginary axis. So that is why we have no damping in the oscillations. So the oscillations are maintained as it. And when the delta value is between 0 and 1, we have the poles on the left half of S-plane. So the poles lie on the left half of S-plane. So there will be oscillations, but it is a damping oscillation. So the oscillations decreases as time goes on. And for a critically damped system, we have two poles at same locations on their axis. So that is the response will be something like this without any oscillations. And when delta is greater than 1, there are two different locations on the real axis on the left half of S-plane. So that is why the response is without any oscillations, and it is called over-damped system. So this is the effect of different damping for a second order system. So when the damping factor value is 0.1, there is large oscillations. So the waveform will have large oscillations, and as it reduces, say 0.5, it has a lesser oscillation. Magnitude of the oscillation is less, and for 0.8 it is even less, and for 0.1, sorry, and for 1 it will be without any oscillation. So that is how the effect of delta on the response of a second order system. So for a second order system with a delta value close to 1 will have lesser oscillations, and far away from 1 will have more oscillations. Now to summarize, we have seen the second order system exhibits a diverse transient behavior based on damping and the frequency. Now, the key matrices in analyzing and designing of the control system is to determine this damping ratio and the natural frequency of oscillation. So we can adjust the demand. We can satisfy the demand based on by adjusting this damping ratio and the natural frequency of oscillation. So the understanding of this response is essential to have effective control system design. How we can design a controller, say PI, PID controller, to satisfy our demands. So we will see a few examples of the second order system and how the response is calculated, how peak overshoot or settling time or rise time is calculated for a second order system for particular parameters of the second order system. We will see that in the next video. Thank you.